In this video, we're going to learn about representing substances that contain more than one type of atom, compounds. Compounds are represented using chemical formulas that contain more than one element symbol for the multiple elements within the substance. These have some conventions associated with them, and we're going to start bridging the gap from the symbolic area of chemistry, the way we represent substances using symbols, and the submicroscopic, the way we think about the substance existing on the level of a single molecule, atom, a single chemical species, really. And so our big goal for today is to represent the number ratios of atoms in a compound using a chemical formula. Chemical formulas contain more than just the element symbols. They also include numbers that tell us about the relative numbers of each type of atom within kind of the fundamental defining unit of the compound, which might be a molecule or something else called a formula unit. We'll touch on that a little bit later, the difference between those two. So, if we get right into it, let's begin with this question: what is a chemical species? We typically use this term chemical species when we're thinking about very, very general principles. And this is very common in introductory chemistry. You'll learn things about the submicroscopic world that apply whether the particle of interest is a single atom, a molecule, an ion, monatomic ion, polyatomic ion, etc. So we use this umbrella term chemical species to refer to all of those things, these submicroscopic particles that define a substance. These are the substance-defining particles, as I say on the slide, chemical species, atoms, molecules, ions, etc. In the first bullet here, I mentioned that when two or more types of atoms find themselves in a compound, they're typically engaged in what's called a bond, which is a linkage between the two atoms. There's some kind of phenomenon that's holding the atoms close in space, and this is what we call a bond or a chemical bond. And that collection of bonded atoms with a good bit of empty space between that collection of atoms and the next collection of atoms over is what we call a molecule. On the bottom of this slide, you see four representations of different types of chemical species. On the left, we have just a sphere-looking thing. This is typically used to represent a single atom, like a single atom of argon, for example. This circle with a plus in the middle indicates a positively charged ion, an ion with positive, or sometimes you'll hear it just called plus charge. The third representation here has multiple spheres linked by lines or sticks that are connecting the spheres. This ball and stick representation is very typical of molecules, and this is a molecule right here. You'll also see molecules represented in kind of a space-filling way where the spheres are generally larger and they're overlapping with each other to indicate a bond. So here, for example, in this dibromine molecule, we have a bromine atom here, and this overlap indicates a chemical bond between the atoms. We'll see these submicroscopic representations. Again, the point for now is that these are all examples of chemical species, and we typically use this word species when we want to describe a very general phenomenon that applies whether we're thinking about an atom, molecule, or ion. Now, these pictures are kind of unwieldy to draw, right? Not very non-artist friendly, and so we really need a textual representation of these submicroscopic images of atoms, molecules, and ions, and this is where the chemical formula comes in. A chemical formula lists the types of atoms in a substance, or ions, using element symbols, and sometimes charges, although charges are often omitted from chemical formulas unless there is a net charge in the particle or species of interest, as well as the number of each type of atom or ion using subscripts. So element symbols indicate the types of atoms in the substance, subscripts indicate each number of that type of atom. And it should be emphasized here that chemical formula refers to the defining species of a substance. In other words, that smallest particle, be it an atom, ion, or molecule, that really defines the substance. If we disturbed that particle, if we changed that particle, we would have a completely different substance. In this way, that particle is the smallest defining unit of that substance. For example, this molecule is the defining unit of glucose. If this is chemically modified, if this group is replaced with another set of atoms, that is a completely different substance. If this is broken apart into multiple molecules, completely different substances, right? And so this is what we mean by substance defining. This is the species that defines the substance. Now, we'll see this in a couple of slides. If we have a grouping of atoms that appears multiple times in that submicroscopic representation in the same form, for example, the same ion appearing maybe 2 or 3 times, we use parentheses and a subscript to indicate that entire grouping of atoms is present in 2 or 3 copies with a subscript 2 or 3, for example. We'll see that a little bit later. At the bottom of this slide, I've added chemical formulas for each of the types of species that we looked at on the last slide. So for an atom, for a neutral atom of an element, it's as simple as the element symbol. This is the element symbol for argon, absolute classic, right? For this cation, the element symbol Na tells me that this is a sodium cation, and the superscript plus indicates the charge. We use a superscript to the right of the element symbol to indicate positive or negative charge. Now for the glucose molecule, which is quite a bit more complicated, we have multiple different types of atoms connected in various ways. The simplest way to represent the chemical formula of this substance is just to group all of the carbon atoms, all of the hydrogen atoms, and all of the oxygen atoms, and use subscripts to indicate their numbers. And so if you take a minute, and it's worth taking a minute, pausing and counting the different types of atoms in this molecule, the first thing we want to recognize is the carbons are dark gray or black, the oxygens are red, and the hydrogens are white. Take a minute and count up all the different types of atoms you see in this molecule. What you'll notice is there are 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms, and the subscripts in the chemical formula indicate that. C6 is the way we read it. That indicates 6 carbon atoms. H12 indicates 12 hydrogen atoms. O6 indicates 6 oxygen atoms. So to the right of the element symbol, a subscript indicates the number of that type of atom in the chemical species. Br2, another example of a molecule, much simpler. We have 2 bromine atoms linked like this. This subscript 2 indicates the 2 bromine atoms, and the Br element symbol indicates that we're talking about bromine atoms here. Let's work through an example of a somewhat more complicated substance to deduce its chemical formula from this submicroscopic representation. Calcium phosphate is the name of this substance, and it's a compound that contains 3 calcium cations, or Ca2+, and 2 phosphate anions, PO4 3-. Now, there's no way to infer from the ball and stick representation or the space-filling representation we see on this slide that the charges are +2 and -3. You kind of have to take my word for it that at this point. What we can do, though, is count the different types of atoms to deduce, for example, there are 3 Ca2+ in a formula unit or molecule, quote-unquote, of this compound, and there are 2 PO4 3-, and within each of those I have 1 phosphorus atom, that's in orange at the center, and I have 4 oxygen atoms bonded to the phosphorus sort of on the periphery. So overall, I have 3 calcium cations and 2 phosphate anions, and so in the chemical formula, the cation is listed first. We'll return to this when we talk about nomenclature a little bit later, but the cation is listed first. And we're going to group those 3 calcium cations with a Ca subscript 3. The charge is omitted since overall, we'll see at the end of this process, we're going to have a neutral charge. The 2 PO4 ions, PO4 3- ions, are grouped together in parentheses, and because there are 2 of them, we use a subscript 2 after the closing parenthesis to indicate that there are 2 copies of the phosphate anion in here, again omitting the charge. This is typically done because the compound is neutral overall, and I do have -6 from the 2 PO4 3-, right? -3 times 2. And I have +6 from the 3 Ca2+, but usually when we're concerned with the neutral compound, which is a solid ionic salt, we don't care that much about the charges, since the compound as a whole is electrically neutral. So you'll see the formula written as Ca3PO42 is how we would read this. Let's talk now about this distinction between a molecule and a formula unit. So back when we looked at glucose, we saw that glucose is composed of intact, discrete molecules like this, right? There are zillions and zillions of these molecules in any macroscopic sample of glucose, but there is a good bit of empty space between adjacent glucose molecules, and we can identify them and characterize these molecules as distinct and separate from each other. In other types of substances, in ionic salts, for example, we actually don't see this structure at the submicroscopic level. What we see is an infinite lattice of repeating units containing just a few atoms. And so they're all packed in so closely together, and they're ionically bonded to each other in the case of an ionic solid. And so it's almost like the substance as a whole is one big molecule. All of the ions are ionically bonded to each other in a very, very large network. And in fact, covalent bonds can behave the same way. And so it's not exactly correct to talk about a molecule in this context, a molecule of the substance, right? But there is a repeating unit that shows up in there over and over and over again, and that repeating unit is what we call a formula unit. In fact, we've already seen this in the previous example with calcium phosphate. Calcium phosphate is an ionic solid, and if you were to zoom in on any macroscopic sample of calcium phosphate, you would see zillions and zillions and zillions of these repeating units with 3 calcium ions and 2 phosphate ions. That repeating unit is not a molecule, since there's an infinite lattice of those cations and anions in the ionic solid. Instead, this is what we call a formula unit. And this is an important distinction when we're visualizing substances at the submicroscopic level, since discrete molecules are very much separate from each other, whereas formula units we don't want to think of as separate from the rest of the substance. A great example of this, and a very simple example, is sodium chloride, which has the chemical formula NaCl. This is an ionic compound, an ionic solid consisting of sodium plus cations and Cl minus anions, and here I'm representing the sodium plus cations in green and the Cl minus anions in purple. And that is the repeating unit, right? If you stare at this long enough, you'll realize all the substance is just an infinite lattice of Na plus Cl minus, Na plus Cl minus, Na plus Cl minus. And so the simplest unit within the very large lattice of ions is one Na plus and one Cl minus, which we can put together into the chemical formula NaCl. It's important, though, when you're looking at this representation, to actually work backwards to this visualization, realizing this is an ionic compound. You'll learn principles for inferring that a chemical formula refers to an ionic compound in your introductory chemistry course, or a covalent compound for that matter. And so you'll be able to go from this chemical formula to this visual or submicroscopic representation. And when you do, it's worth keeping in mind that what this is a representation of is not a discrete molecule, but the formula unit. A few lingering questions now about chemical formulas. One question is, how do we determine these things in the first place? How do we measure the number ratios of atoms in a compound? They're extremely small. How in the world do we think about making measurements with these? You'll answer this question in your introductory chemistry course. If you look at the formulas of ionic salts, many ionic salts, for example, that you can buy from a laboratory supplier, they often include formulas like this with, for example, .6H2O after copper and sulfate. What's going on here? What does the dot mean, and why are there 6 waters incorporated into this chemical formula? How do we visualize those waters? Where are they? What kinds of bonds are they involved in? What do the molecules look like? Questions like this. The third lingering question is very interesting. There are compounds that contain a fractional or decimal ratio of atoms. How is this possible, given that we can only have discrete numbers of atoms at a time within a compound? And the answer is there's heterogeneity in these compounds when you get down to the submicroscopic level. They don't look the same everywhere, and this leads to fractional or decimal, so-called non-stoichiometric compounds. You may or may not see these in your future work in chemistry, but they're very interesting to think about on the submicroscopic level, since they kind of lack a fundamental repeating unit, or if they have one, it's very, very large. It contains a very large number of atoms.